Hello, and welcome to Examine Earth. Today, we're going to investigate a new answer to an old joke. What's worse than a giraffe with a sore throat? A centipede with sore feet. Ugh, that's certainly bad, both the symptoms and the joke, but I think it's been topped. How about a sauropod with a soro throat? This question is inspired by a recent paper, so let's go take a look. The paper appears in February's issue of Scientific Reports. This is Nature's fully open access journal that covers a wide range of science topics. It's freely available to everyone, even without a subscription or access to a university library. Paywalls prevent the spread of information and are anti-science, so I'm glad to see that. The title is the first occurrence of an avian-style, that's bird-style, respiratory infection. Boy, aren't we sick of those? In a non-avian, not bird, dinosaur. The authors are a truly multidisciplinary group of paleontologists, osteologists, and imaging experts. First author Kerry Woodruff is the director of paleontology at Great Plains Dinosaur Museum. He's published extensively on dinosaurs, and especially the sauropods. Co-author Matt Wedel has also written a deep dive in a series of blogs, which I'll link below. This video is my attempt to summarize their paper and findings, along with some more basic background information. If you already have extensive knowledge in this area, it might be best to go right to the source. The reason this discovery is so notable is that the fossil record mostly only records the hard parts of organisms, things like bones, teeth, or shells. There are a lot of things that can happen to an animal's remains before it fossilizes. Taphonomy is the study of these various effects. Everything from the time of death all the way to preservation as a fossil, or much more often, not being preserved as a fossil. A standard respiratory infection impacts only soft tissue, which rapidly decomposes. However, this infection was severe enough that it impacted the dinosaur's skeleton. This provides a rare chance to examine the impacts of a dino disease. You can see here in figure 3 from the paper, the red arrows marking where germs could migrate within the throat. They used a silhouette of Dr. Fauci for scale, so you can see that this is a big throat. You can see air going in through the trachea to the lungs as expected, but you'll also see some additional air sacs in the body and even along the neck. We'll discuss these structures in a bit, but first, why is this such a rare and noteworthy discovery? Well, respiratory diseases are all too common, as we're all still experiencing. They're common in humans, but birds can also suffer from these diseases, despite the differences in our anatomy. Modern birds are avian dinosaurs, so if birds can suffer from these diseases, could the non-avian dinosaurs also? Up until now, the answer was probably, but now it seems like yes. But why did it take this long to find an example? Wood et al. Described what they call the osteological paradox in 1992. Some animals will just not be impacted by the disease. Lucky, or maybe they were dino distancing. Many others, most others maybe, will catch the disease, but for a soft tissue disease to start impacting bone, it must be severe. So many of these animals will die from the severe illness before it impacts the bones. Still more will recover either quickly or slowly, and the damage will heal. In all of those cases, no trace of the disease will be preserved in the fossil record, only with this odd sweet spot of severe illness, severe enough to eventually spread to the bone, but not severe enough to kill quickly, but it does need to kill before healing, so it's a pretty narrow window and makes this a truly unique discovery. Let's take a look at our dinosaur patient. Dolly was a diplodocus. Named for Diplodocus. In addition to their long sauropod necks, they're known for their even longer whip-like tails. In fact, the name means double beam for the odd double row of bony extensions on the underside of that famous tail. In Dolly's lifetime within what's now the Morrison Formation, she would have coexisted with the very common carnivorous Allosaurus. There were also some larger but rarer carnivores around, so that whiptail probably came in handy. It also helps to be big, like really big, more so even than modern elephants. Fully grown and healthy sauropods were probably just too large for even the boldest and hungriest of carnivores. Allosaurus likely targeted the very young, very old, or very sick. Is that what killed Dolly before she healed from her sickness? Let's take a look at how sauropods breathe. Unlike our cyclic breathing with large lungs and a muscular diaphragm, birds have a more continuous airflow. Their many smaller air sacs, in addition to the lungs, provide all that oxygen needed for sustained flapping. Even many of a bird's organs are enclosed by air sacs. In fact, much of their body cavity is filled with air sacs, and their bones are also specialized to provide conduits. The soft tissue air sacs and conduits of dinosaurs would not be preserved directly. However, we can see evidence of their size and placement from the shape and structure of the bones. This is pretty similar to how we can reconstruct musculature from the hard part muscle attachments, even without the muscles themselves. In birds, all this air powers flight, and it keeps them light. We don't usually think about sauropods as light, but the air sacs keep them lighter than they should be. This helps them reach tremendous sizes. Whichever animal was the largest to ever walk the earth, it was some species of sauropod. Which sauropod depends on how you define large. If you mean longest, it was probably a diplodocid similar to Dolly. If you scaled an elephant up to sauropod size, it would crumple under its own weight. If you double the height or length, that increases the surface area by 4 times and the volume or mass by 8 times. This is Galileo's square cube law. Giant mammals like King Kong, robots like Pacific Rim, and insects like them just don't work. They're too heavy for their support structures. All of the air sacs keep sauropods much lighter for their size than elephants are for their size. The efficient bird-like breathing also helps to get rid of heat, which elephants also struggle with. Their large ears act as radiators to dump excess heat, and you often see them taking mud baths or staying in the water to cool down. This elephant-like model led early paleoartists to depict sauropods in water, as in Fantasia. It was assumed that they could not support their own weight and needed to stay in water. This concept still persists with ideas that sauropods need to breed in water in what's come to be infamously referred to as sex lakes. That's a pretty absurd restriction and almost certainly not true, but still, it's pretty funny. At the height of the sauropods during the Jurassic, there was also more food available. The world was warmer and wetter than today and had an estimated 2 to 3 times more productivity. An elephant can eat up to 300 pounds of food in a single day. Sauropods would have needed to consume multiple times that much. A real-life Jurassic Park would really struggle to feed a sauropod population. So all this air and food helped Dolly reach her tremendous size, but it also led to her infection. Let's look in more detail at the evidence of the infection. Here's a dorsal looking down from above view of a pigeon. Compare this to the dorsal views of Dolly. You can start to see just how similar they actually are, despite being very different animals. This is evidence of their shared evolutionary heritage. We can't see the evidence of infection within the body cavity, but we can in the neck. Here, the air passages were in close contact with the bony vertebrae. We can also see that the lesions are not random, but occur on both sides of 3 different vertebrae, specifically the cervical vertebrae, numbers 5 through 7. It's probably also significant that the infection occurs a little farther up the neck. These areas are more distal, farther from the lungs, where circulation is very likely slow. It's not being actively pumped as we think of breathing, but with slower diffusion. The pathogens could linger in this area and lead to the advanced infection. Looking closely at an individual vertebra, we see a bulbous lesion of pathologic bone. We can also see some odd surface pitting related to the severe infection. This is not just the first documented evidence of this type of infection in dinosaurs, but it also adds to our understanding of dinosaur respiration. We can see direct evidence of the bird-like respiration in the development of this infection. The authors have done an amazing job in presenting their research, and it's also amazing that it's available via open access. In addition to the paper itself, they've also communicated their work on blogs and through popular media. It's an excellent example of effective science communication in the modern digital age. And I hope that I've added some more basic background information here with my video. If you want more sauropod information, please check out my free Dinosaurs video course. Up here somewhere is a link to the Sauropoda video, and also in the description below. This video discusses sauropod anatomy and behavior and highlights several different sauropod species. If you enjoyed this video and would like to see others like it, please click the like button and subscribe to the channel. You can also let me know in the comments below what other topics you'd like to see. That's all for today. Thanks for stopping in to examine Earth.